Antiderivatives, or indefinite integrals. Let's start with the motivating question. Suppose you were given a velocity function, v of t equals cosine t, and you were asked to find the position function, s of t. So essentially what we have to do is think about what function do I have to take the derivative of to get cosine t out as the answer. So if you're thinking s of t equals sine t, that is definitely a function of which when you take its derivative, you get cosine t out as the answer. But the question is that the only possible answer? What if I add 2 to the function sine t? When I take its derivative, I still end up with cosine t. So this idea of thinking about what do you have to take the derivative of to get a particular function out as the answer is the topic known as finding antiderivatives or indefinite integrals. Let's define what an antiderivative is. A function, big F of x, is an antiderivative of little f of x on the interval from a to b if big F prime of x equals little f of x for all x in the interval from a to b. So essentially, what we're saying is that capital F of x, big F of x, is an antiderivative of little f of x if, when you take its derivative, you get to this function little f of x. So in this example, find, and here's a key word, find an antiderivative for f of x equals 2x. So we're thinking about what is a function that I can take the derivative of and get 2x out as the answer. Well, hopefully the answer or unanswer is pretty clear. X squared is a possibility. So this is correct for this particular example. Find an antiderivative. Well, this one will work. If I take its derivative, I do end up with 2x. But there's a whole family of answers, and that idea is really expressed over here in this graph, where we can see that not only x squared, the parabola x squared is drawn. If I add any constant behind x squared, when I take its derivative, I still get out 2x. Now that constant being added to the outside of a function is really just a shift, either up or down, to the original function x squared. So we can see two other antiderivatives, x squared plus 2 or x squared minus 2, so just shifts in the graph of x squared. Now we generalize this idea by defining the general antiderivative. So let big F of x be an antiderivative of little f of x on the interval from a to b. Then every other antiderivative on the interval from a to b is of the form big F of x plus c for some constant c. So now we are generalizing this idea of the antiderivative. In this example, find the general antiderivative for f of x equals 2x. So now the only difference is that it's x squared plus the generic constant c. So we're not picking a specific shift in x squared. We're generalizing it to say some constant c. So this is the general antiderivative. In this next example, we're going to do something slightly different. We're going to find the antiderivative of f of x equals 2x that satisfies big F of 1 equals negative 1. So what we know is that the general antiderivative, big F of x, is x squared plus c. So I want the specific antiderivative that satisfies this condition, that when I plug 1 into the x value, what comes out is negative 1. So I want f of 1, well, that would be 1 squared plus c. I need that to equal negative 1. So I'm solving this equation here for the constant c. So in other words, this is 1 plus c is equal to negative 1. And if I subtract the 1 from both sides, I get a c value of negative 2. So the specific antiderivative that satisfies this condition would be the antiderivative big F of x equals x squared minus 2. And this process of finding the antiderivative is called antidifferentiation or integration. Indefinite integral. A general antiderivative is also called an indefinite integral. And here's the indefinite integral notation and then terminology to go along with it. So here, this symbol is the integral sign. So this right here is called the integral sign. And it is, too, an operation. It's telling you to take the antiderivative of this function here, which is called the integrand, and then dx is the differential, so we have to take the integral of the integrand f of x, and the differential says what variable to take the antiderivative with respect to. And then big F of x is the antiderivative, and then c is the constant of integration. So these are all of the terms associated with an indefinite integral. The power rule for integrals. If we want to find the antiderivative of a power function x to the n with respect to the variable x, we're this time going to add 1 to the exponent. So we have x to the n plus 1, and then we divide by the new exponent n plus 1, and we need our constant of integration, our plus c. So this only works where n is a real number, but n cannot be -1, because then we would be dividing by a 0 here. So we can't divide by 0. So here are some examples of applying the power rule for integrals. So we have a variable in the base, a number in the exponent. So we are going to add 1. So I'll go ahead and show the work for the first one, where I'm going to add 1 to the exponent, and then divide by that new power. So I'm going to divide by 2 plus 1, and then I have plus c. So simplified, I have x to the third over 3 plus c. And if I think about this just real quickly, if I take the derivative, I would bring that power to the front, so the 3's would cancel, and then I'd subtract 1 from the power to get out x squared, or the integrand. So we can always take the derivative of our indefinite integrals and see if we get the integrand out as the answer, and then we'll know we've done it correctly. So now here I have the integral of x to the 3/2. So I'm going to add 1 to the exponent. So if I add 1 or add 2 over 2, I'm going to get x to the 5 over 2. And then I divide by the new exponent. So divide by 5 over 2 plus c. But here, I don't want to leave a complex fraction, so instead of dividing by 5/2, I can think about it as multiplying by the reciprocal, so I have 2/5 x to the 5/2 plus my constant c. And then finally here, I'd have to do a little bit of rewriting first, so I'm going to rewrite this as x to the -2 dx in order to apply my power rule. So I'm going to go ahead and notice I kept the indefinite integral, or the integral sign here, so I haven't actually done anything besides rewrite the integrand yet. So now I'm going to apply the power rule for integrals. I'm going to add 1 to the exponent, so that's going to make it a -1, and then I divide by -1 plus c. Or a little bit more simplified here, I'm going to end up with -1 over x plus c. So I'm just thinking about x to the -1 moving to the bottom and moving the negative sign to the top. So sorry about working so low. I have -1 over x plus c. So we have a sum or difference rule similar to derivatives, where if I'm trying to find the antiderivative of f of x plus or minus g of x, I can take the antiderivative of each piece separately. And I also have a constant multiple rule where I can take any constant, any number, outside of the indefinite integral or the general antiderivative. So here, we're going to go ahead and look at a few examples. So first, I'm going to go ahead and rewrite this so that I can apply the power rule for integrals to each piece. So I have 2x cubed is set up perfectly for me, so I'm going to leave that. And I'm going to rewrite this as x to the 1/2, and then I have 3. So I haven't taken the antiderivative yet, so that's why the integral sign is still there. So if I'm going to go ahead and apply the power rule, well, the constant just kind of stays. So I have 2x to the 4th. Remember, I'm going to add a power and then divide by the new power. And then we'll go ahead and have minus x to the 3/2. So I added 1 to a half, and then I divide by 3/2. And then plus, well, here I have just a constant. Now remember, we're not taking the derivative, we're taking the antiderivative. So here, I mean, what's really going on is I can think of it as a 3x to the 0. So if I think about adding 1 to the exponent, I'm going to get 3x to the 1, and then I would divide by that new power, right? So I would divide by that 1, and then plus c. So in other words, if I just have a number, I just have to put the variable behind it. So just 3x. So I showed all the work here applying the power rule, but it's simply if I have a numerical value, I just add the variable to the back, or multiply by the variable behind it. So a little bit more simplified, this is 1/2 x to the 4th minus 2/3 x to the 3/2 plus 3x plus c. And for the second example, the first thing I would need to do is multiply all of this out because I need everything added or subtracted. So I don't have a rule that allows me to take the integral of each piece of a product separately in the integrand. So I have to distribute everything out. So I'm going to have 2x squared. Here I have minus 4x plus 3x, so minus x minus 6. dx. So I have not yet actually found an antiderivative. I'm about to, so I'll have 2x to the 3rd over 3. So I'm adding a power, dividing by that new power. Here I have an x to the 1, so I'll have x to the 2 divided by 2. And then here I just have a constant, so I would simply put an x behind it. So if we think about that, the derivative of negative 6x is negative 6. And then plus c. And in this example, there's really no simplifying that can be done. So this is my indefinite integral. So here, just a really important warning that was mentioned a second ago. If I have the integral of a product, I cannot simply take the integral of each piece separately and multiply them. And I cannot take the integral of a quotient as the integral of the numerator over the integral of the denominator. So those are not properties of indefinite integrals or general antiderivatives. And in fact, there is no equivalent rule like how differentiation has the product rule or the quotient rule. We actually don't have those for integration. It's going to be a little bit tougher, and we're going to get into those strategies a little bit later. So besides the power rule, we are able to formulate a list of general antiderivatives based on our knowledge of derivatives. So the integral of e to the x is e to the x plus c, since the derivative of e to the x is e to the x. I also have another form. I have e to the kx plus b. So this would be e to specifically a linear function. So kx plus b is linear, like mx plus b. So if I have this particular form, then the antiderivative is 1 over k e to the kx plus b, and then of course that plus c for the constant. So here what would happen if I took the derivative of this side, I would have to apply the chain rule, and I'd get that k being multiplied in the front to cancel with the 1 over k. So this is kind of just a unique form of the integral of e to a linear function in the exponent. The integral of sine x is going to end up being negative cosine x because, of course, the derivative of cosine is negative sine, so I need a negative to cancel. Of course, plus c. And then again, here's that sort of general form where I have sine of a linear function. There's that kx plus b again, so what has to come in the front is that 1 over k cosine of kx plus b, with the overall quantity being negative, and then plus c. And the integral of cosine is positive sine plus c because the derivative of sine is cosine. And if I have that linear piece inside kx plus b, I have to have a 1 over k in front. We have further integrals involving trig functions. The integral of secant squared is tangent x plus c. The integral of cosecant squared x is negative cotangent x plus c. The integral of secant tangent is secant x plus c, and then finally the integral of cosecant cotangent is negative cosecant x plus c. So all of these come from our derivative properties. And then finally, some further general antiderivatives, if we remember our inverse trig derivatives. So the integral of dx over 1 plus x squared, or we can think about this as 1 over 1 plus x squared dx, so that differential can also be written in a numerator. Well, that's arctangent x plus c, because the derivative of arctangent x is 1 over 1 plus x squared. The integral of 1 over radical 1 minus x squared dx is arcsine, and of course if there's a negative, then we have arccosine. The integral of an exponential function, a to the x dx, well, that's a to the x divided by natural log a, as opposed to for the derivative, it's multiplied by natural log of the base. And then here we have the integral of 1 over x dx, or another way to see it is the integral of dx over x. Well, that is the natural log function of the absolute value of x plus c, where of course x cannot be 0. All right, now let's combine the power rule and all those general antiderivatives by finding the integral of 2x to the negative 3 plus e to the negative 2x plus secant squared x minus 1 over 1 plus x squared dx. All right, so here, all of these terms are being added or subtracted, so we can do each one separately. And the first one we'll do by the power rule for integrals. So we have 2x to the negative 2, because I'm going to add 1 to the power, and divide by the new power, negative 2. And now here I have e to the negative 2x. So the general antiderivative is e to the negative 2x, and then what has to go in front is a negative 1/2. So that k value is negative 2, so it's 1 over k. So that 1 over negative 2. And then plus, well, the derivative of tangent gets me to secant squared, so we have plus tangent x. And then here I have minus 1 over 1 plus x squared. So there's actually two different things that you could put here. We could write, because we see this 1 over 1 plus x squared, we might think arctangent or tan inverse. So we could write minus tan inverse or arctangent of x plus c, of course. But I'm going to put the other variation below it. We could also have written this as plus, and it would be cotangent inverse of x. So negative 1 over 1 plus x squared, if we remember from our derivatives, was the derivative of cotangent inverse of x. So that's another variation, but we'd have to just make sure to write plus cotangent inverse of x. So we can just do a little bit of simplifying. If we cancel out these 2's, we can write this as negative 1 over x squared, and then minus 1/2 e to the negative 2x, or we can bring the e to the negative 2x to the bottom of this fraction, plus tangent x, and I'll just leave it as tan inverse, minus tan inverse of x plus c. So this is now just combining the power rule for integrals, and some of our general antiderivatives. In this example, we want to take the integral of 3 over x squared minus 3e to the x plus sine 3x plus 3 to the x. So first, we're going to go ahead and do a little bit of rewriting. This first term here, we want to rewrite as 3x to the negative 2 so that we can apply the power rule for integrals. And all the rest are fine for us to just jump in and find each of their general antiderivatives. Alright, so now applying the power rule for integrals here, we have 3x to the negative 1, if I add a power, divided by that new power, negative 1. And now here, I have this constant, this negative 3, just comes on down in the front, and the antiderivative of e to the x is just e to the x. And now here I have plus sine of 3x. So I have this linear piece on the inside, this 3x. So what's going to end up going in front is that 1 over k, that 1 over 3, and we are going to have cosine of 3x, and we just want to make sure the sign, like positive or negative, is going to come out correctly here. So if I take the derivative of cosine, I'm going to get a negative, so that means I have to have a negative here to cancel that out and get me back to this positive sine 3x that I want. So we're going to have negative 1/3 cosine 3x, plus this exponential is 3 to the x over natural log of the base, natural log of 3, plus c. So a little bit of simplifying here. I'm going to rewrite this as negative 3 over x minus 3e to the x minus 1/3 cosine of 3x plus 3 to the x over ln 3 plus c. So this is my general antiderivative. In this next example, before we start, I want to remind you of this general antiderivative. The integral of 1 over x dx equals the natural log of the absolute value of x plus c. This is very specific that we need x raised to the first power here. I need 1 over x specifically for the answer to be the natural log of the absolute value of x. Now, one of the most common mistakes in integration is when students see 1 over something, they automatically turn it into natural log of the absolute value of that something. But it has to be just an x in order for this to actually work. So in other words, what I see a lot of is in this type of problem here, I see this 1 over 5, this 4 over x. I see these variables on the bottom, or on this one, not even a variable. But sometimes what I've gotten in the past, and I'm going to do it in red to indicate that it's incorrect, like stop, is I've gotten natural log of the absolute value of 5, plus 4 natural log of the absolute value of x, plus 2 natural log of the absolute value of x squared, plus natural log of the square root of x plus c. This is mostly wrong. The parts that are incorrect are this one, and this one. So the only one where the answer really was a natural log of the absolute value of x was this second piece here. So we were able to think about that constant being on the outside. This is the only piece that's correct here. So all of the rest of this is incorrect. So I'm going to go ahead and erase it. Hopefully you did not write it down because it is wrong. And we're going to go over how would we evaluate this indefinite integral here. So I have the integral of here 1/5, so that's just a constant. And then here I do have 4 over x. So this is 4, I'm going to write this as 4 times 1 over x. And then, so this one will again turn into that natural log of the absolute value of x. This third piece we can rewrite as 2x to the negative 2. And the last piece we can write as x to the negative 1/2. So these two pieces are going to use the power rule for integrals. And this first piece is just a constant, so we're just going to put the variable x behind it. So what I have, I left the integral sign because I've only rewritten it. I haven't actually done an integral yet. Now I'm going to drop the integral sign and write 1/5 x plus 4 times natural log of the absolute value of x. Remember that constant can just stay outside. and the integral of 1 over x is ln, absolute value of x. And then for this next piece, I have plus 2x to the negative 1 over negative 1. So I'm adding 1 to the power and dividing by that new power, plus x to the 1/2, if I add 1, divided by 1/2, plus c. And if I simplify, I get 1/5 x plus 4 times the natural log of the absolute value of x minus 2 over x. So I just brought that negative outside, dropped the x to the negative 1 to the bottom, and then plus here I would get 2 radical x. So if I multiply by the reciprocal, it's 2, and then x to the 1/2 is square root of x plus c. So this is the correct answer. And just a real quick aside, sometimes, people do forget the 1 over x is natural log of the absolute value of x, and they'll try to use the power rule. So I just want to show what happens on just that piece if you try to use the power rule. So if you have 4x to the negative 1 dx, and I try to rewrite it first and apply the power rule, I'll get 4x to the 0 divided by 0. So remember that we can't divide by 0, so the power rule didn't apply in this particular case because there is a different answer. It's natural log of the absolute value of x. So this wouldn't work, and hopefully you'd see that if you tried it and remember what the actual antiderivative is. So let's just take a look at some common mistakes. If I have the integral of a function raised to a power, I cannot apply the power rule for integrals, so I can't just raise that whole function to the n plus 1 and divide by n plus 1. So for example, something like this, 2x squared plus 3 squared is not 2x squared plus 3 to the third over 3. So what I would have to do in this example is multiply this out. 2x squared plus 3 times 2x squared plus 3. So I have a bunch of terms added and subtracted, so I can do each one separately. And the other common mistake, this is the one I just mentioned, if I have the integral of dx over f of x, that is not just always the natural log of that bottom function in absolute value bars. So in other words, if I have something like this, 1 over x cubed plus 3, that is not just natural log of x cubed plus 3. And in fact, this is not a problem that we can solve with the tools that we have yet. So just to be clear, we cannot just take the natural log of the denominator when there's just a number on top. That's not the antiderivative. And there is a main idea going on with antiderivatives or these indefinite integrals. So if we take the derivative of big f of x and we get out little f of x, well, then that means the integral of little f of x is big f of x plus c. But the big f of x, little f of x notation may be a little bit hard to understand because it's the same letter, just in, capital versus lowercase. So here's another way to think about it. If I take the derivative of g of x, that's g prime of x. So that's the equivalent to saying the integral of g prime of x is equal to g of x plus c. So if you can sort of notice what's happening here, I'm taking the integral of a derivative and getting back to the original function g of x, of course, plus some constant c. But that's the main idea behind what we're doing in these general antiderivatives or indefinite integrals.